So up until now, we've only had one named distribution. It's the z-distribution. Again, z meaning standard normal. It means a normal distribution with a mean of 0 and a standard deviation of 1. Next, we're going to talk about a t-distribution. The student's t-distribution is also a normal distribution. It also has a mean of 0. However, it has a standard deviation larger than 1. And the idea is that we are going to use a t-distribution when we have data from a population with an unknown standard deviation. And this is one of those things where that statement can sometimes seem a little bit weird. And so I just want to focus in on the when do we use the t-distribution. If we know the population standard deviation, we use a z. If we don't know the population standard deviation, we're going to use a t. And your first question is almost assuredly, how do I know if I know that or not? The idea is that now we are into the inferential statistics portion of this course. And if you remember from way back, like the second slide we had in this course, we've discussed from there moving forward, and I kind of stopped saying it because we got focused in on our probability questions, but let's come back to the key phrase that I kept saying a lot, which was the whole purpose of this course is I don't know something about a population. And so what do? I take a sample and I use the data from that sample to make an inference on that population. And that's what we're about to start doing. Okay, we're about to start doing it via hypothesis testing. And what we're going to do is we're going to say, I don't know the population mean, or I don't know the population proportion. And then we'll expand on some of these ideas as we move on deeper into the course. But let's just start off with our two basic concepts, the ones that you've seen before. If I don't know something about a population mean, or I don't know something about a population proportion, what do? I take a sample, and I'm going to take a sample mean or a sample proportion, whichever one is appropriate, and I'm going to use that to make an inference about said population mean and population proportion. This is why that definition at the start of this chapter was important, that point estimate idea. When we don't know what the population mean is, I take a sample, I take that sample mean, that's the point estimate. That's my best guess at what the population mean is. But just because it's my best guess, how confident am I in that, right? And so as we begin to make these inferences, we have to say, okay, I didn't know the population mean. I took a sample and I found the sample mean, but do I know the standard deviation of the population? Okay, so make sure you catch that. It's the idea of I don't know the population mean, so I take a sample, I get the sample mean, I use that to make an inference on the population mean, but do I know the population standard deviation? And the answer to that is almost assuredly in that scenario that you don't. Because if you recall back in chapter 2, the definition for the population standard deviation had the population mean in it. So it seems a little far-fetched that you would not know the population mean. The whole point of what we're doing is we don't know the population mean, so we're going to work with the sample mean and use that to make an inference. But you somehow knew the population standard deviation, which its formula requires the population mean. You see how that seems a bit far-fetched. And so when we work problems with a mean, we're going to say almost assuredly, 99 times out of 100, we won't know the population standard deviation. And so because we won't know that population standard deviation, that's what leads us to using a t-distribution, which is very similar to a z. Right? A z is a normal distribution, a t is a normal distribution. A z has a mean of 0, a t has a mean of 0. However, a z has a standard deviation exactly equal to 1, and a t has one larger than 1. Okay? And then we have to say, what about the population proportion case, right? In a population proportion case, there is no, the standard deviation is not a separate entity. If you recall, in a proportion case, we worked through all that hairy math with the binomial, and we said that the standard deviation actually is just a function of p's and q's and n's, right? And so in that case, we can actually deduce the population standard deviation. We don't call it that, right? Because it's just a bunch of p's and q's and n's. That's that square root formula that was so nasty. And so in a proportion case, we say we actually kind of can figure out what the population standard deviation is. We have a formula for it. And so in the proportion case, we're going to stick with that z. It's nicer. But in the mean case, we're going to have to use a t because we are not going to actually know that population standard deviation, because the only way to know that is if we actually knew the population mean as well. Now, there are an infinite number of t distributions. And that should kind of make sense based off the definition, because notice I said a standard deviation larger than 1. How many values are larger than 1? There's an infinite number of them, right? A t distribution is any normal distribution centered at 0 with a standard deviation larger than 1. So standard deviation of 1.52, 2.53, whatever. Those are all t distributions. Okay, there's an infinite number of them. Each one of them has with it associated a degrees of freedom. Now, this definition I have in small font. That's because I don't need you to memorize the definition of degrees of freedom. I'll let you read it. It's kind of a weird concept. It's related to the idea of why when we had sample standard deviation back in chapter 2, we divided by n minus 1 rather than n. You don't need to know the ins and outs. It's a more of an advanced idea. Degrees of freedom is a very important concept, though, that you need to understand. Every t distribution has a degrees of freedom with it. For the one sample mean problems that we're going to start off with, the degrees of freedom are equal to n minus 1. However, we're going to see different setups where the degrees of freedom will be different later on. We're going to see a set-off hypothesis test later in this course where the degrees of freedom, we're going to use a t, but it's actually equal to n minus 2, not n minus 1. And I'll talk about why when we get there. And we're going to see different distributions that are not the z, not the t, that also have degrees of freedom, not equal to n minus 1. And we're going to have one distribution that has 2 different degrees of freedom with it. It's not just one number, it's actually 2. So you don't have to memorize the definition for degrees of freedom. That's not why I don't want you to write it down, because I don't want you to think you had to memorize that. Just understand that when we get to these non-unique distributions, what I mean when I say that is the z is unique, there's only one of them. When I say normal, mean of 0, standard deviation of 1, I've uniquely identified it. When I say a t distribution, I know it's normal, mean of 0, but I don't know what its standard deviation is. I haven't uniquely identified it. There's a lot of them out there. So any of these distributions that are not uniquely identifiable, there's a lot of them out there. They all have some form of this degrees of freedom that are associated with it that helps us identify it. That's the last piece of the puzzle to actually tell us what it actually is. Okay, and we're going to start off with these one sample mean problems. We're going to have degrees of freedom equal to n minus 1. Okay, as we move forward in the course, we'll talk about when that's going to change, why it's going to change, etc. We're just going to start off with this using a t-table, one sample mean, degrees of freedom are equal to n minus 1. So, an example, find the critical values for a 95% confidence interval for a t distribution with samples of size 3 and 12. So, let's pop on over to our t-table to figure this one out. Now, the thing that you'll notice here with the t-table that works different from the z-table is that it works exactly backwards, and it only has one tail of the distribution. Why is that? There, as we've talked about, are an infinite number of t distributions. And so because of that, we can't make one table for all of the t's. Instead, we have to make one row for all of the t's. And they could have flipped it, made it columns, but they didn't. They decided to make one row for each one. And that's what you'll see on that first column of degrees of freedom, listed down 1 through 40, and then it does 50, 60, 80, 100, and 500. And so it's telling you, first off, you need to discover which t you're working with. Again, for the one sample mean, we find that by n minus 1. That leads us to our degrees of freedom, find the appropriate row. And then rather than having an entire table, instead what they have done with the t-table is said, really, we know that you only care about certain things. You probably don't care as much about all of the little intricate details, how to find, significance levels of 3% or 6% or stuff like that. We really just care about the main ones. And so that's what you see on that those top 3 rows there. You'll see confidence levels, we talked about, it's 1 minus the significance level. But then you also see one-tailed and two-tailed area. That's significance level. Now again, for this chapter, we're just focused on two-tailed area. We're going to split that alpha into both tails. But when we get to a one-tailed scenario, you would look at that row. And you just find the intersection of the appropriate significance level and degrees of freedom, and that's your critical value. Notice though, as the picture illustrates at the top, it is only showing you the right-tailed area, as opposed to the z-table, which does less than. So again, everything's backwards with the t-table. So we want to make sure we have a good understanding of the z before you really start diving into the t. So if you're still a little bit behind on that z, just pause this, go back, refresh yourself on that, and get good footing there, because everything goes wonky when you look at the t. It's everything different than the z-table does. And so you'll only see positive critical values. It's because it's only got that right-tailed area. If you use a two-tailed, if you're in a two-tailed scenario, you would just have to add the plus and minus on there. If you're in a left-tailed scenario, you would need to add the negative yourself. If you're in the right-tailed scenario, boom, you've got your answer. And that should then allow us to answer the questions in this example, finding critical values for a 95% confidence interval. Again, that means 5% significance level for a t-distribution given those sample sizes. So we start off, if we have a sample size of 3, first thing we have to do, find the degrees of freedom. It's going to be 3 minus 1 is 2, and so we're looking on the second row of that table, and we're looking for, again, 5% in the two-tailed area, and that should get you to 4.303. Again, we're going to add on the plus or minus. Notice how I've notated here. How you notate is not extremely critical as much as I'm just trying to notate things so that you can understand, you can follow along. We've put the asterisk up here to indicate that this is a critical value, and then we've subscripted with the degrees of freedom. Why is that? Because I can't just say t, because then the answer or the question becomes, which t are we talking about? So in this case, I'm saying, I'm talking about the t with 2 degrees of freedom, and that critical value, in this case, would be 4.303. Do the same thing for sample size 10, it should be 12. Subtract 1 to get our degrees of freedom of 11 and find that row. We get plus minus 2.201. And then I have a note here that I want to make sure that we talked about here, that when you compare these to the z critical values, these are both larger than that. Typically, if we had been trying to find the critical values using a 5% significance level, a z-distribution, we would have said plus and minus 1.96. You can find that by the bottom row of the t-table. It says infinity degrees of freedom. We'll talk about that momentarily. But the idea here being that this is what is supposed to happen. This is what we want to have happen. We want larger critical values when using a t rather than a z. You say, wait a minute, that's kind of confusing. Why do we want a larger critical value? What does it matter? Well, if we go back to the idea that we talked about at the start of this, which is we use the t when we have data from a population with an unknown standard deviation. The idea is we don't know something. There's more uncertainty there. And so then the next logical step to I'm dealing with a little more uncertainty means when I use this critical value, remember a critical value being a cutoff point to tell me what's unusual versus not unusual, what's likely versus unlikely, it just means I want to give myself a little bit of a buffer there to say, yeah, but we have some more uncertainty, so I don't want to be quite so harsh when determining what's unlikely. And then further, you will see here that as my sample size gets bigger, my critical value gets smaller. That should also make sense because if you recall back to the start of the previous chapter, we talked about the law of large numbers, which said the bigger my sample size, the more accurate my statistics are in estimating parameters. And so it's this idea that if we don't know the population standard deviation, what do? Well, we would have to use the sample standard deviation in its place as its estimate. Law of large numbers says really big sample size means that's a great estimate. Small sample size, not a great estimate. And that's what you're seeing here. You can take a look at that t-table and you can see this example playing out as it is here in this little example that I've done for you, in that the bigger the sample size, the smaller the critical value gets, the more and more we just get to use the Z critical value. But when we have a small sample size, I need a bigger critical value. Again, why is that? Because if I have a small sample size, if I'm estimating the standard deviation with a sample size of 10 or 5, law of large numbers would say that may not be a very good estimate. So I need to make that critical value bigger in order to compensate for that. But when I have a really big sample size, we say the law of large numbers says that even though I don't have the population standard deviation, my estimate, the sample standard deviation, ought to be pretty good. And so if it is pretty good, then that means I might want to make that critical value a little bit bigger because I don't really know how good it is, but I may not have to make it that much bigger. So some important properties of the t-distribution. All of these things we've kind of covered to some extent. I just want to make sure they're all formally written down. The first one, there are an infinite number of t-distributions, one for each possible value of degrees of freedom. The t-distribution is a normal curve. It's the same symmetric bell shape as the z. Okay, so I'm just kind of saying that in different words just to make sure we're all on the same page here. The t and the z are both normal distributions. They're both symmetric and shaped like a bell. But it's going to reflect greater variability. What that means is the tails are thicker in that distribution. And that's why those critical values are a little bit bigger, right? It's going to reflect thicker tails, bigger critical values because there's greater variability, because if I don't know the population standard deviation sigma, I'm having to estimate it with that. That's what we just talked about here with why do we use a t? Well, we use a t when we don't know what sigma is. If we don't know the population standard deviation, by having to estimate it with S, we have to say, oh, there's a little bit of uncertainty here. That's why we use the t, and thus that's why we get greater critical values, right? And that's the whole purpose of this. The t-distribution, just like the z, has a mean of 0. But unlike the z, its standard deviation varies, number 1, and number 2, it's always greater than 1. And then the last thing is that thing I talked about that we'd come back to at the bottom of that t-table is that if my degrees of freedom approach infinity, as they get larger and larger and larger, the t basically becomes the z. It approaches the z distribution. It's the idea that if I had a t with degrees of freedom of 9,000 or 15,000, the critical values are going to be so close to the z. At that point, you might as well just use the z. And that's what that bottom row is trying to indicate to you. And you see that with the row of 500, how those values are really, really close to the z critical values. It's saying, as my degrees of freedom, or, again, because degrees of freedom and sample size are so closely related, as that gets larger and larger, the t-distribution is basically the z-distribution. Now, as a side note, depending on where you might have seen statistics before, this is the reason that sometimes teachers will say, if my sample size is large enough, we can just use the z-distribution. That's not what we want to do. We want to use the t-distribution because it is technically accurate. So if you've seen that before, it's totally okay to understand this concept, but actually using the z as a shortcut is not something that is recommended. So it's this idea that if you did have a sample size of 2,000, and we have an example in our notes later, in chapter 9, where we'll have a sample size, I believe, of 2,500, really, really large. And it's like, yeah, we could basically use the z because it's the same thing at that point, right? Yes, that's true. But what we want to do instead of focusing on that is getting into the habit of saying, if we don't know the population standard deviation and we have to use S instead of sigma, that's when we use the t. Ignore the sample size. You can know in the back of your head, if my sample size is really big, it's going to be basically the same thing that I would have got from the z, but that's not what we are focusing on. We're focusing on if we don't know sigma and we have to use S, that's when we use the t.